Okay, good morning, everyone. Let's start. So first of all, we have released the due for your project choice and project proposal, and the Kaggle computation task has been released like since last week, and the due for your your project choice and team, and also proposal is on, I think it's 27th this month. I think that should be enough time for you to, to try the Kaggle stuff or think about your interesting exploratory ideas. But we do need some deadline for you to make a decision. So if you haven't started, you haven't thought about what kind of project you want to do, please start thinking about right now. And if you are unsure about, for example, some explore project choice, you're unsure if this topic sounds interesting, if that topic it makes sense, feel free to come to the office hour and discuss with me or discuss with our TAs. Okay. Okay. So let us continue with the decision tree learning algorithm. So in the last lecture, we first talk about in detail this basic and popular decision tree learning algorithm called ID3. Right? So ID3 is a recursive algorithm, namely by recursive calling itself, it kind of hierarchically partition the data set into many small subsets. At the same time, create new tree nodes and grow new branches until all the leaf nodes are created. Right? So now that it is a recursive algorithm, so we discussed, right? So to design a Yeah, we're about to that point later, but we mentioned that before, right? We want to do the discretization first. We cannot directly deal with continuous or numerical feature values, but that's a good point. We will return to that point later, right? So now let us first quickly review the ID3 algorithm we discussed in last lecture. So, so as we mentioned, because it's a recursive algorithm, so the very first important step we need to figure out is what is the base case or what is the stopping criteria, right? You cannot keep calling yourself to grow your tree to infinite large. You're gonna exhaust the system's resource, right? So when should we stop the tree growing? Of course, one obvious stopping criterion would be if all the examples have the same label, right? We mentioned that if all the examples share the same label, and then we should will this node as a leaf node, right? And then we use that label as the label for that leaf node. So we create a leaf node, we return a leaf node with that label. And also there's a subtle corner case we should account for. That is when the attribute set is empty. Namely that even if your data set S is yet being uniquely labeled, but you have exhausted the attributes, meaning that you don't have any attribute to further split on S, then you have to stop as well, right? And it's not uncommon in practice. Like if you have like 1 million training examples, but you only have 10 attributes, it is likely that even you have used up all 10 attributes, you still cannot partition your data set into uniquely labeled subsets. Right? In that case, you have to stop. And then you also return a leaf node, but you're going to pick up the most common label in S as the leaf nodes label. Okay? So those are the stopping cases. The control, it tells when the tree growth should stop, right? And otherwise, it means that, okay, we can safely expand our tree. How can we do that? We first create root node for the tree, which corresponds to S. Then among the available attributes here, we're going to pick up an attribute that best splits S, and later we'll return to the point, what do you mean by best, right? But once we have selected a best attribute A, we're going to look at every possible value that A can take, right? And we partition the data set according to A's values. And for each particular value V that A can take, we create a new tree branch, attach the testing condition here, whether if A is V, right? And then we look at the subset of examples whose A attribute takes value V, which we denote by SV, right? So here we talk about another corner case, right? We actually mentioned several times, like if SV is empty, right? Meaning that, okay, no examples in S whose attribute A takes value V, right? It is possible when we use some manual construction, right, for a set of color shapes, right? And here we emphasize that even if SV is empty, we're going to still create a leaf node. And we use the most common label in S as the label for this leaf node. The reason of doing this is to make your decision tree to be robust, right? Otherwise, if you got some test example where you go through from the root, right? You go to this test branch where A equals to V. If you don't have a leaf node, you don't know how to give a prediction, right? So you must ensure that in every possible test case, you're gonna reach to some leaf node and can provide some prediction, right? That's the reason, right? And otherwise, if SV is not empty, and then we expect that we can further create new tree nodes and branches by splitting on SV, right? So how can we do that? This is the convenience of recursive programming, right? We can call ID3 again, right? And now the current subset will be SV, and we're gonna exclude attribute A from attribute set because it has been used, right? And then we call ID3 again, then you can imagine it goes to the same kind of routines to decide whether we're gonna stop at SV and create leaf node, or we further create branch and partition SV according to some other attribute, and so on, so on. Right? So this is a whole algorithm procedure. And then a critical step in this algorithm framework is the attribute selection procedure, right? So in the last lecture, we spent quite an amount of time talking about what do we mean by best splitting the data set S, right? So talk about this is essentially a greedy strategy. Namely, the best attribute is the one when we use that attribute to split data set to get a list of subsets of examples, right? We can best improve the label purity, right? So why should we measure the utility or measure the best features in that way? Because if every time we can pick up an attribute that best increase the label purity, we expect that we do not need many attributes to split on data. We only need a few steps. We can make all the subsets to be uniquely labeled. And consequently, we expect that our tree structure will be small, right? So our goal is to make our tree to be as small as possible. Why? Because we want to follow the so-called Occam's razor principle, right? We want our tree to be as small as possible. I mean, if you have 10 trees and each tree can equally well represent data set, we want to pick up the smallest tree, right? This is called Occam's razor principle. Namely, without necessity, we don't want to increase the model complexity. And again, this is a philosophical principle, but turns out to be very effective and successful in numerous engineering and scientific disciplines, right? So then the problem is that how do we measure the purity improvement after using this attribute to split data set, right? So we have some kind of intuitive examples to show like how should we compare the goodness of these features in terms of label purity, right? But we do need some quantifiable metric, right? And so what kind of metric should we use, right? I have to say, like, there are are different metrics. There's no like absolute choice for one particular metric because the purity, label purity can be measured in different ways, right? So we start with the classical metric called information gain, which was used in the arranged ID3 algorithm, but later we're going to introduce several variants, right? So information gain is based on the definition of entropy. Entropy is a term in the information theory. But basically, you can will entropy as a way to measure the uncertainty about labels in your data set. So it's interesting to see that entropy and label purity are actually kind of like two sides of a one coin, right? So the larger the entropy, meaning that the more uncertain you feel about the labels, which implies that these labels are more mixed, right? More evenly distributed, which means that the label purity is low, right? On the other hand, the smaller the entropy, meaning that the less you feel uncertainty about labels or more confident about labels. And when do you feel more confident about labels? If those labels are very biased, like 99% are positive, 41% negative, well, I can say, okay, I'm pretty much sure it is positive, right? So in that case, it means your label purity is high, right? So you can see that entropy, label purity are kind of like two sides of a coin. So if we want to evaluate the increase of the purity, we can calculate the decrease of the entropy, right? Or the reduction of the entropy. That's the logic. So here's the entropy, the rule, the formula of computing the entropy with just the definition. Like for binary labels, if you have you have p positive, p negative, denote the proportion of positive examples, proportion of negative examples. If you have a k classes and p1 to pk is just the proportions of each class, then the entropy is computed by just minus p positive logarithm p positive minus p negative logarithm p negative, and this is always non-negative, right? Why? Because those proportion is between 0 and 1, right? The logarithm is negative and you have negative sign outside of log, so it's negative gives positive, right? And in general, if I have a k classes, the entropy is defined as negative summation of pi logarithm pi. And those are just concrete examples showing the entropy's properties and how it reflects the purity of the labels. I'm not gonna repeat this, right? So now we return to the definition of the information gain, right? So as we just mentioned, right, we want to look at, after using a particular attribute A to split on data set, how much purity improvement can we get? Or in other words, how can we evaluate the expected increase of purity, right? So we evaluate this kind of purity increase by information gain, which is the expected reduction in entropy, right? How can we compute that? We first compute the entropy of the data set before split, right? S, right? We just compute the entropy of whole data set S. And now, once we use attribute A to split on data set, we know that, okay, according to how many distinct values A can take, it was split into several subsets, right? And now we compute the entropy of each subset. Now we do some weighted average of those entropies according to the size of each subset, right? And why would we like to reweight the subset entropy according to their size? Any thought? Yeah. That's a good question. But let us just hold off. I want to ask, why should we reweight those entropy of each subset after splitting? Yeah, exactly. Yeah, I just don't want everyone to review what we have discussed, right? So because the size of each subset can vary, right? Of course, a large size is viewed as more important, right? So we need to review them, and of course, reweighting is kind of based on proportion. It's a size of SV divided by the total size of S, right? So this that's why we call it expected reduction, right? And return to our problem. Yeah, you're right. In actual computation, you never need to explicitly compute the entropy of a whole data set because you want to rank the information gain, right? And those are common factors. It doesn't change the rank. Yeah, but here to ensure the integrity of this whole concept, we just illustrate. Okay, this is how we compute information gain. But in your homework, in your programming, you can ignore the computation of entropy of the whole data set for sure. Okay. So entropy of the partition and data is calculated by weighting the entropy of each partition by size relative to the original set, which explains this part. Right? So now we subtract the expected entropy of the splitted subsets. We subtract the entire entropy of the data set S by the expected entropy of the splitted subsets, we get information gain. Right? So every time we just look at all the available attributes, your current attribute set, then you calculate the information gain of every available attribute. Then you look at which attribute gives the largest information gain, which meaning that, okay, using that particular attribute, you're gonna split the data set, then you're gonna best improve the label purity. Okay, okay, so far, any questions? Everyone feels comfortable? Okay, now we're going to use concrete examples to illustrate how we inject information gain in ID3 algorithm to construct our full tree. Right? So I highly suggest everyone after this class manually do this and compute the information gain, rank those features, and replicate this tree construction procedure. That will be very helpful in understanding the algorithm details, and very helpful for your homework one. Okay. So this is our data set. We got 14 examples, and the label is whether I play tennis or just stay at home, right? According to 4 temperature attributes, right? Outlook, temperature, humidity, weather attributes, right? We got 4 weather attributes like outlook, temperature, humidity, and wind, and each of which takes a few different values, right? So now at the beginning, right? Imagine that you are now a machine, right? You want to run ID3 algorithm. At the beginning, you start a root node, right? And you want to pick up a best attribute out of these 4 available attributes to split on the whole data set, right? And then we need to compute information gain, right? We're gonna figure out which attribute gives the maximum information gain, which we believe that attribute will be the best. We're going to use that one to make the first partition of the data set. Right? So how can we compute information gain, right? As we just mentioned, we need to first compute the entropy of the entire data set. The entire data set consists of 14 training examples where 9 are positive and 5 are negative. So we got P positive, 9 over 14, right? P negative, 5 over 14. Then we just apply the formula to compute the entropy, minus P plus, logarithm P plus, minus P negative, logarithm P negative, which gives you 0.94, which is the entropy of the entire data set. Right? So now, let us look at the information gain of using outlook feature to split on this data set. Right? So because outlook can take 3 values, right? So meaning that using outlook can partition the data set, it results in 3 subsets. We're going to compute the entropy of each subset, then do a weighted average, and then subtract the entire entropy to get information gain, right? That's follows the definition of the information gain, right? So let us first look at the subset examples where the outlook attribute is sunny, right? So if we look at this data table, we got 1, 2, 8, 9, 11. Those examples all take sunny outlook, right? So we just look at this subset and look at the entropy, right? So from these 5 examples, we found that 1, 2, 2 are positive, and all the remaining are negative, right? So that means the P positive is 2 over 5, and P negative is 3 over 5. Just apply the entropy formula again. You can get the entropy for this sunny subset is 0.971. Right? And then we'll look at another subset where the outlook takes the value overcast. Right? So if we look at all the examples whose outlook is overcast, you can see that example 3, which is positive, example 7, which is positive, example 12, which is positive, example 13, which is positive. You can see that all 4 examples are positive. So what's the entropy? 0, right? We mentioned that if the data set is unique labeled, then entropy is the minimum, which is simply 0, right? Okay. The third one will be the subset examples whose outlook attribute is raining, right? So you see that there are 5 examples, right, where 3 of them are positive and 2 of them negative. Then you apply the entropy formula again, you can get the entropy 0.971 as well, right? Which is the same as this guy, right? So now we have computed the entropy of each subset. Then we do a weighted average according to the size of each subset. So the sunny subset, the size is 5, so 5 over 14 times 0.971, their entropy, plus the second subset, outlook overcast subset, we got 4 examples, so the weight is 4 over 14, and entropy is simply 0. And third one, 5 examples again, is 5 over 13, which is the weight multiplying with the entropy here. So then you can get the expected entropy, which is 0.694. Okay. Now, to compute the information gain, we just subtract the entropy of the entire data set by this expected entropy after splitting, right? We got 0.246. Whereas this is a kind of like expected entropy reduction. On the other hand, it's kind of expecting improvement of the label purity after you use outlook to split this data set, right? Okay. Have we finished? Now, yeah, right. We just compute the information gain for one attribute, outlook, and we have 4 candidates. We need to compute the information gain of all the remaining attributes, and then look at who is going to give the best information gain, the largest information gain. Then we'll choose the one who gives the largest information gain to split the data set. So following the same procedure, we're going to compute the information gain of humidity. Right? So if you look at this data set, the humidity attribute takes 2 values, right? One is humidity is high, right? For all the high humidity examples, you will see that all of them are positive, right? Which are here, here, and here. Okay? And the remaining 4 are negative. So you have P positive is 3/7, and P negative is 4/7. Also, by the way, there are total 7 examples whose humidity is high. Right? So then apply the formula. You can compute the entropy to be 0.985. Right? And another subset of using humidity for splitting is the normal humidity. Right? So there are another 7 examples whose humidity is 7, and from this subset we see that 6 examples are positive, only 1 example is negative. So got P positive 6/7, P negative 1/7. So the entropy is 0.592. Okay? So now you can compute the expected entropy, which just reweighting those subset entropies according to the size gives you 0.7885. Right? Now, to compute the information gain, we subtract the entropy of the entire data set by the expected entropy, right, which is 0.1515. Right? So it's quite mechanical. You follow the same procedure to compute the information gain of the wind attribute, which gives 0.048, and temperature, which gives 0.029. Right? So now we have computed information gain of all the attributes available to split on the current data set. Right? So which one should we choose? Outlook, right? Obviously, Outlook gives the largest information gain, meaning that if you use Outlook to split on data set, you can best improve the purity of those labels in the splitted subsets. Right? Then we have made decision to use Outlook to partition our data set and grow a few branches in our tree. Right? This is where at this stage, what does our tree look like, right? You got 3 branches, which corresponds to Outlook is sunny, Outlook overcast, Outlook is raining. So here we just list the indices of these training examples in each subset, right? Meaning that example 1, 2, 8, 9, 11, whose Outlook is sunny, 3, 7, 12, 13, whose Outlook is overcast, and the remaining whose Outlook is rain. Right? So now we're gonna recursively call ID3 algorithm over each subset, right? And to say if we're gonna continue partitioning on each subset to grow more tree nodes and branches, or just to stop and create leaf node. Right? So for convenience, let us just look at the middle one. So imagine that, okay, here when you recursively call ID3, you will test first the base case or stopping criterion, right? You see that, okay, all the examples have the same label, which is positive, meaning that it's not necessary to partition this data set anymore, right? You should create a leaf node to represent this data set, and the label is just positive. So now you stop growing here, right? But for the other two, the sunny subset and the raining subset, we found that, okay, they haven't yet reached the stopping criterion, right? Meaning that, okay, we're going to still partition each subset from the remaining available attributes, right? So let us look at one by one. Right? First, let us look at the sunny subset, right? So here is the table of the sunny subset. There are 5 examples in total, 1, 2, 8, 9, 11, right? So look, all the Outlook attribute take sunny. So that means the available attributes to further split on this subset will be temperature, humidity, and wind. We should exclude the Outlook feature. Right? That follows the algorithm design, but it's also reasonable. Why? Because all the Outlook attribute takes the same value. Right? How can you use that to further split on data? Right? We can only take a look at the remaining 3 attributes. And then follow exactly the same computational procedure, right? You can compute the information gain of using humidity to split on this sunny subset gives you 0.97, right? And again, the computation procedure, first compute the entropy of these 5 examples, right? And then look at, okay, if I use humidity, I can partition the data set into 2 subsets and then compute the entropy of each subset and do the weighted average to get expected entropy and calculate the difference between the whole entropy and the entropy of this whole set and the expected entropy over the subsets, right? You get information gain. Right? It's just follow the same procedure, right? You can compute the information gain of humidity splitting on S sunny, meaning this 5 examples will be 0.97. And the information gain of using temperature to split this subset gives 0.57. And information gain of using wind attribute to split on this subset gives 0.02, right? So which one should we use to further split sunny subset? The humidity, right? Because humidity gives the largest information gain, meaning that it should best improve the label purity after using humidity for splitting. Okay? So for the left subset, sunny subset, we're going to use humidity to split the data set. And the good thing is that, okay, we found every subset is unique label, right, by some label, right? So that means we further get 2 leaf nodes, right? The left one leaf node contains all the negative examples, which labels no, right? And the right one contains all the positive examples, right? And so the label is yes, but we haven't yet finished. If we can recall, actually, the range of humidity contains 3 distinct values. Right? You got high humidity, you got normal humidity, and you got low humidity. Right? So although the sunny subset doesn't have any example whose humidity is low, meaning that, okay, if I use low to look at the subset examples, it's simply an empty subset, right? But we cannot ignore it, as we mentioned, right? We need to cover all possible test cases. So here we'll create a new branch, right? And a leaf node for the case where humidity is low. And then we pick up the most common label in its parent node, right? So the most common label will be negative, right? So the label for this leaf node is no. Does it make sense? Right here, just to showcase how this corner case we previously discussed taking effect here, right? And then we see that because all those 3 nodes are leaf nodes, we stop growing at this place, right? And now we'll return the recursive calling of this ID3 pop. You can imagine, computer science domains should be like pop up the stack, right? And finally, you will move to the recursive calling of this ring subset, the right subset, right? You got another 5 examples which are not uniquely labeled. So you're gonna recursive call ID3 again to partition this subset, right? And again, we need to compute the information gain of all the remaining attributes, right? And this time, the attribute wind takes the highest information gain. So we pick up wind to partition the ring subset, right? So, and we'll see that why it is reasonable to pick up the maximum information gain, because if you use wind to partition on the data set, you see all the subsets are uniquely labeled. So you give 2 leaf nodes. So now we have finished the tree construction. Any questions so far? Can we still use what? Yeah. You still need to compute the information gain of humidity splitting on rain, wind splitting on rain, and what is the other guy? And temperature. right? But in this case, right, for the ring subset, it turns out that the win attribute has the largest information gain. That's why we choose win to split the ring data set. Other question? Yeah, because overcast here, it is already represents a leaf node. You no more split. Right? If it is a leaf node, we just give a label on the leaf node. We never need to consider any new attributes to split on that. And only when we split some kind of other data set, right? And when we split that, we found out, okay, for some attribute value, no one in this subset takes that value, meaning that the corresponding subset is empty, but we still need to preserve that branch and create a leaf node accordingly. Why? Because if we not do that, we're going to miss some test cases, and you cannot guarantee a reasonable prediction for every case. And we need to guarantee the robustness of or comprehensive or coverage of our decision tree classifier. Other question? You got confused of computing information gain over the Sunday subset? Okay, so at this step, right, we have already selected outlook to split on data set, right? You end up with 3 subsets, right? But those Sunday subset and ring subset, they are not unique label, meaning that we're going to still need to split on them, right? And then the question is that from the remaining attributes, temperature, humidity, and wind, which one should we use to split sunny, and which one should we use to split rain data set, right? And how can we select the attribute? We need to compute the information gain again, right? Oh, it's just follow the same procedure. Like you got this, we take this sunny subset as example, right? You got 5 example. And according to the definition of information gain, we're going to first compute the entropy of this entire data set, which only contains 5 examples, right? You can look at P positive, P negative, right? You apply the formula, you get entire entropy, right? And now if we take a look at humidity's information gain, meaning that, okay, I'm going to use humidity to split this subset, which gives you 3 high humidity examples, 2 negative humidity examples, right? These 2 subsets. For each subset, you look at P positive, P negative, compute entropy, and then you do a weighted average of those entropies, right? And now you subtract the entropy of this entire subset by the weighted average of the subset entropies. You get the information gain. It just follow the same procedure. Does it make sense? Any other question? Oh, great. So, yeah, the whole procedure looks kind of like a maybe look simple or relatively straightforward, but I still suggest everyone to manually do this. I'm not saying that you need to manually take logarithm over 1.5, something like that. You can use calculator for sure, but I just want you to follow the definition of the information gain computation and the selection of those attributes, and then to manually replicate the construction of this tree. And it will definitely give you a very good understanding of our ID3 algorithm and also the information gain computation. Okay. Can you say it again? So always been active. Which one? The low? Oh, okay. You mean why we give a negative label? Oh, so we don't have any examples in the subset to show which is positive, whether it's positive or negative, right? Because it's empty subset. So we're gonna go back to look at its parent node. So this Sunday subset. We just look at which label is the majority label in a parent subset. Okay. Any other question? Oh, that you need to specify the range of the attribute values. Otherwise, if you just infer the range of the attribute from the training data set, of course, we cannot cover that case. Right? Here we assume that, okay, we know the instance space, right? The instance space specify, okay, which particular attribute, which particular set of values each attribute can take, right? And then you can look at this corner case and create branches. Otherwise, you won't be able to do that. Yeah, that's a good point. Okay. Any other question? Great. So summary of the learning decision trees. So first, we introduced the representation of decision trees, which is essentially a hierarchical data structure that represents data. Then our algorithm of learning decision trees, which is essentially tree construction algorithm, right? This is a greedy heuristic, and the greedy heuristics use the following rules, right? If all the instances have the same label, create a leaf node with that label. Otherwise, we find the best attributes and split data for different values that attributes take, right? And then we do the recursive calling to split on the splitted data sets, right? So here are the we finished discussion of the major topic of the decision trees. Then the remaining thing about the decision tree is we're going to give some discussion about practical usage of decision trees. You see that in practice, only just implementing ID3 algorithm is often insufficient. You have to deal with some annoying cases. So first, we're going to introduce several variants of decision tree. Variants meaning that we can pick up a different measurement of label purity, not only using information gain. Right? We're going to introduce several other commonly used label purity measurement as alternatives. Right? And the second one is very important. We're going to discuss how to handle examples with missing feature values, which is pretty common in practice. And in practice, you won't imagine that, okay, you have a perfect data set and all the examples all the attributes are good and are there. You can just throw them into some off-the-shelf machine learning algorithm. You always need to do some like pre-processing to deal with noisy, missing attributes or even missing labels and so on. Right? We're going to talk about the several important strategies to deal with missing feature values. And then we'll talk about non-Bloom features, as someone asked, right? How can we deal with numerical features, right? Continuous features. And finally, we're going to introduce the concept of overfitting and why overfitting is so annoying in machine learning practice, right? And what kind of harmonies it can bring. Okay, here is our ID3 algorithm again, right? We mentioned that the very important or critical component is that at every step, how can we pick up the attribute that best splits the data set S, right? So the best split here, we mean, okay, after using that attribute to get a list of subsets, we can best improve the label purity. And how do we measure the label purity improvement? We mentioned that the one classical metric is called information gain, right? But information gain is not the only one which can be used. for this, right? And we can use other variants. One particular simple variant is called majority error. So what's the definition of majority error? Suppose the tree was not growing below this node, right? So we got a set of examples, and which are mixed label. And then if I use the majority label to predict all the examples, what is the prediction error? This is called majority error. Like at some node, we have like 15 positive and 5 negative examples. Then what is the majority error? Any thought? What? 1 over what? Yeah, exactly, right? We just apply this literally, right? So majority error means that, okay, I just use the majority label in this data set to predict every example, right? So the majority label here obviously is positive because 15 are positive, right? So if you use positive label to predict all the 20 examples, you're gonna have 5 misclassified examples, right? And then your majority error will be 5 over 20, right? Which is 1/4. Right? This is majority error. So interestingly, majority error also reflects the label purity. Why? Let us consider the extreme case first. Like if all the examples have the same label, what is the majority error? 0, right? If all the examples, for example, all the 20 examples here are positive, the majority label is positive. If you use positive label to predict every example is correct, classified, right? So in that case, majority error is 0, and your label purity is a maximum, right? Unique label. Right? On the other hand, when the majority error is the largest, equally distributed, right? The label is equally distributed, right? So imagine that for these 20 examples, you have 10 positive, you have 10 negative, right? Then the majority error is simply 10 over 20, which is half, right? At this time, your majority is maximum. The label purity is worst, right? Because all those labels are kind of like evenly distributed. Right? So I want to ask, can the majority error be less than half? Is it possible that you got like 0.3 majority error? What? Oh, sorry, more than half. Yeah, sorry, it's my bad. Yeah, yeah, more than half. It is possible you got 0.7 majority error. No, why? Yeah, because you're using majority label, right? If you're using majority label means that, okay, the majority label at least take more than half of the examples, right? Or at least half of examples, meaning that the error of, or the proportion of misclassified examples with majority error will be less than or equal to 50%, right? So that means majority error will be always less than or equal to half, right? So that's why only when positive and negative examples have the same number, you got the maximum majority error, which is half, because majority error cannot be bigger than half. Yeah, then that one won't guarantee like it'll be less than half. But you can imagine, you can think about which one, what is the maximum value the majority error can take. But in whichever case, we can see that majority error can reflect label purity as well, right? Then majority error is maximum, meaning that your labels are evenly distributed, you have a worst label purity, right? On the other hand, when the majority error is simply 0, minimum, right? Then your label purity is the best. Right? All the examples have the same label. So therefore, we can view majority error as kind of counterpart to entropy. Then we can use the larger the majority error, the worse the purity, right? The smaller the majority error, the better the purity. So again, to measure the increase of the label purity, we can look at the expected reduction of the majority error. So this is how we compute the so-called majority error gain. Right? Mm-hmm. No, how can we? No, you cannot. You cannot do that, right? How do you see majority? Like if you're a continuous number, how do you define majority? But here, let us just restrict our scope to the classification problems. For the regression problems or regression trees, it's not the major focus of our class, but you can make some like simple variants on that. We're gonna have some discussion about that later. So following the majority error, we can compute the majority error gain, right? Which is actually the same structure for the information gain, except that we're going to replace the entropy by majority error. On all the other steps are the same. Like if you want to compute majority error gain, you first compute the majority error of whole data set S, then you use this particular attribute A to split on the data set to get a bunch of subsets, right? You compute the majority error for each subset, you do the weighted average, and then you subtract the global majority error over S, and you get majority error gain. You can use that to pick up the best attribute for splitting as well. Is everyone comfortable? Okay. Let us look at another variant. Okay. So, and this is another alternative to information gain, which is called the Gini index. Okay. So Gini index is also very popular in constructing decision trees. So what's the definition of Gini index? So if we have binary labels, the Gini index is simply subtract 1 by p positive square plus p negative square. Right? If you have like a k labels, right? So when p1, p2 to p big K, which are the proportion of each labels, right? And then we just subtract 1 by the sum of squares of each p1, p2 to p big K. Right? So this is called Gini index. So let us look at how Gini index reflects the purity. So first, when Gini index is the smallest, yeah, just look at this. We just look at the binary case because the multi-class case follow the same logic. Yeah, P1, either P1 is 1 or P0 is 1, right? Then the Gini index will be the smallest. And then in that case, you have the best label purity. Right? And when the Gini index is the largest, yeah, 0.5, right? When P plus equals to P minus, right? Why? When they are equal, they got maximum Gini index. Yeah, if you remember, right, we actually have learned that kind of equations, inequalities, maybe in our primary school or high school. I forgot. Anyway, so we got some inequality like this, right? Right. So one subtracted will be less than 1 subtracted by P1, P2, right? And when this inequality becomes equality, P1 equals to P2, right? Why? Because if you move this right-hand side to the left, you essentially got P1 minus P2 square no less than 0, right? So of course, when P1 equals to P2, your inequality becomes equality, right? And when P1 equals to P2, meaning that they're both 0.5. Okay? And in this case, you make this guy to be the smallest, and you subtract 1 by this guy will be the maximum. Right? And when P1 equals to P2, P equals to 0.5, you got largest Gini index. Right? At the same time, we got worst purity. Right? Does it make sense? Right? I mean, you can just play around this inequality, right? It's not hard to see this point, right? And in general, you can apply kind of similar equation to that, or you can use convex Jensen's inequality to show that. I will leave it as exercise for you. Maybe it's maybe some like bonus question to show that when all pk equals 1 over big K, you have the largest Gini index, which corresponds to worst purity, label purity. Okay? And of course, when any p small k is 1, you got Gini index is simply 0, and then you have the best label purity. Right? So in summary, the Gini index, like majority error, like entropy, also reflects the label purity. The larger the Gini index, the smaller or the worse the label purity. The smaller the Gini index, the larger or the better the purity. So again, if we want to look at the expected increase of the label purity, we can compute expected decrease of the Gini index. So again, we can use the same structure to compute the Gini index gain. Right? This follows the same structure as information gain, except that we're gonna replace entropy here by the Gini index. Right? So, any questions so far? Is everyone comfortable? Right? Regarding this question, right? For the general case, I believe for the binary case, everyone now is comfortable that, okay, only when P plus equals to P minus, you get largest Gini index. For this one, if you want to show that only when all pk equals 1 over big K, meaning uniform distribution, it gives the largest Gini index, you need to apply some inequality, which can be derived from Jensen's equality we discussed at the very beginning of our semester. Right? And I will leave it as an exercise for you. Right? Of course, it's not necessary for you to prove that, but I'll highly encourage to do that. It's an interesting mathematical game. Okay. So here's just one example. I will just skip it because it's relatively straightforward. Okay. Now let us talk about second topic, the missing feature values. Okay. So in practice, it is often the case that you collect some examples, but some attribute is missing. Right? It's not always the case that, okay, you collect a set of like complete examples, every attribute is properly measured, and so you can simply throw them into your machine learning library. It's not like that. So what if we have some example, like in our tennis playing classifier, we got 15th example, which is negative example, but the outlook attribute is unknown. How can we deal with that case? Right? The simplest approach is just to discard this example. Let us ignore the existence of such an example, and we just use those complete examples in the tree construction. Of course, it's doable, but it's not very good, right? Because we kind of miss one more example, right? Which could be helpful to improve our classifier. Right? If we want to leverage this incomplete example, what should we do? Maximum what? Try to what? Oh, okay. Yeah, that's a good idea, but it's I think it's a little bit more advanced than the things we want to discuss right now. But let's yeah, I want to let you finish first. Yeah. Yeah. That's a good idea. So basically, if I want to unify the points by you two, is that okay? If we want to use this incomplete example, we're going to first infer some value for this attribute. Right? We pretend this value will be the missing value. Now we just complete this example. We just throw them into our ID3 algorithm. It can work normally, right? Then that comes to the question, right? How can we complete that example? In other words, how can we estimate the missing attribute, right? So the simplest one will be, okay, we're going to use the most common value of that attribute in the whole data set. Okay? Like for this example, we might take a look at all the 14 examples, 14 complete examples, because we know that we have 14 complete examples. And we look at, okay, among these 14 examples, how many take sunny, how many take overcast, how many take rain, right? We pick up the most common to fill this blank. Okay? That's one way. The other is to take the most common value of the attributes among the examples with the same label. This seems more reasonable, right? Because this example is negative example, then I have a reason to believe that, okay, the choice of the value of this outlook should be more similar to the values of the examples who are also negative, right? And of course, there are other choices like what you mentioned. We might pick up some median value or some, but here, if we look at just purely categorical values, it's hard to say which one should be ruled as median, which one should be ruled as average, right? But of course, it's numerical values. Yeah, it's one choice. Mm-hmm. Yeah, that's a very good point. This is something I want to bring up. You're exactly right. If you just infer this missing attribute with one value, you actually introduce some kind of bias, right? Although this bias sounds reasonable, but it is not always appropriate, right? So to be more reasonable and to be more robust, right? We want to consider cases that every possible value when this attribute take, what will happen, right? And how can we do this? We can use the fraction counts of the attribute values in the training data. So what does it mean by fractional counts, right? So basically you can think of, okay, for this particular example, I believe the missing outlook can take 5 over 14 sunny value, 4 over 14 overcast value, and 5 over 14 rain value, right? What does it mean, right? And how does we incorporate some fractional counts into our training algorithm? Here's the details, right? So let us look at this 15th example with overlook attribute missing, right? So we want to account for all possible choices of the outlook value it can take, right? That means it can take sunny, overcast, and rain. Then how can we do that, right? We can break this example into 3 fractional examples. And the fraction is based upon the proportion of each possible outlook value take in the whole data set. Okay? So we know that, okay, in the previous 14 examples, whose outlook value are never missing, right? We know 5 of them are sunny, 4 of them are overcast, and 5 of them are rain. So we break them into 3 break this incomplete example into 3 examples and complete the overcast feature in each example with a particular value, and the fraction is the proportion of that value takes in the whole complete data set. So it's 5 over 14, 4 over 14, 5 over 14 sunny example, 4 over 14 overcast example, and 5 over 14 rain example. Doing this, first, we're able to account for all possible cases. Right? Second, we also account for the difference. Right? We know that it's more likely the outlook takes sunny value and rain value than you take overcast value. Why? Because according to what we have seen so far, the proportion of sunny and rain is larger than the proportion of the overcast. Right? And this doesn't change the total data amount, because if we add up these fractions together, it still end up with 1, right? Meaning that you still just increase the number of examples by 1. Does it make sense? Any questions so far? So first of all, does everyone feel comfortable that, okay, I use this way to complete this missing attribute with all possible values? This sounds reasonable, right? It covers all possible cases, and at the same time, it accounts for the different possibilities, the possibilities of choosing different values, right? Then the remaining question is that, how can we incorporate these fractional examples into the original data set and then compute the information gain, the rank, the features, and pick up to split on data set, right? That's something we need to be concerned, right? How can we do that, right? It's actually, we follow the same procedure, right? And except that when you compute the data set size and p positives, p negatives, you have to account for some fractions, right? So this is the original data set, right? 14 examples. And if you use Outlook, you're gonna partition the data set into 3 subsets, right? Sunny, overcast, and rain, right? Now consider we add one more example with this negative example with Outlook attribute missing, right? As we mentioned, we're gonna break it into 3 fractional examples where each example, the Outlook takes a different value, right? So now, if we use Outlook to split on this new data set, right, we can see that the 3 fraction examples will be allocated into the 3 subsets respectively, right? It's because this first fraction example takes sunny outlook, so it will be allocated here. The second one takes overcast outlook, it will be allocated in the middle, right? The third one takes rain, so it will be allocated into a third subset, right? So we want to compute what is the information gain of outlook, right? So first, if we look at the whole data set, previous data set contains 9 positive and 5 negative, right? But the whole data set only includes 1 more example. If you add up all the fractions together, just 1 example, right? So from the whole data set level, we just have 1 more examples, 1 more negative examples. So you have 9 positive and 6 negative. So nothing changed. Nothing is changed when we compute the entropy over the entire data set, right? We can look at the p positive, which is 9 over 15 now. P negative is 6 over 15 now, right? The difference comes from how we compute the entropy of each subset, right? After you use Outlook to split data set. Right? So you can see that each subset now includes some fractional example, right? But essentially, the computation doesn't change as well, as long as you can get used to that. Right? So we know that this first fractional example is added into this sunny subset. So previously we got 5 examples. Now we got 5 plus 5 over 14 examples. Right? So don't consider that those. So now we no longer consider the number of examples must be some integers, right? It can be some fractions plus integers. Right? So it's 5 plus 5 over 14. And then we look at how many positive examples do we have, how many negative examples do we have. We still have 2 positive examples, but we have 5 over 14 negative examples more. Right? So now the number of negative examples is 3 plus 5 over 14. Does it make sense? Right? And similarly, if you look at this, the middle subset, all the examples takes overcast or look. So you got 4 plus 4 over 14 examples in total. Why? Because we have an additional fraction example. Fraction is 4 over 14. And among which 4 examples positive. And then you have this 4 over 14 negative examples. And similarly, for the third subset, we have 5 plus 5, 14 examples in total, where 3 are positive, and 2 plus 5, 14 are negative. So you can see that we can count number of positive, negative, and total number of examples as usual, except that you need to add this fraction into your count. Okay? And once you got this counts, it's fairly straightforward to compute P positive and P negative that are necessary to compute entropy, right? So P positive is just the 2 number of positive examples over the total size, which is fraction now, is 5 plus 5 over 14, right? And P negative is 3 plus 5, 14, which is total number of the negative examples over the size of data set. You got P positive, P negative, you just apply the formula to compute entropy, you get entropy, right? Does it make sense? And similarly, you can compute P positive and P negative for overcast subset as well, right? P positive will be 4 plus 4 over this 4 plus 4 over 14, right? And P negative will be with this fraction over 4 plus 4 over 14, right? And then you just apply this formula to compute entropy as well. So you mean you change the label to be positive? Why do we choose the conditions of? Yeah, based on missing information. So the fraction is computed by the proportion of each feature value in the complete examples. Oh, I just random fabricate such an example. It can be arbitrary other choices, as long as you collect from some applications. It's not necessary to be mild, high, weak. It can be other values. Yeah, it's just a strategy. It's just a strategy. It can be any other, like it's not necessarily mild. It can be, I don't know what's the other choice of. I forgot. But it's like high. It could be low or it could be normal. This could be strong or weak. It really depends. But here we just want to discuss what kind of strategy, how we complete the missing all of attribute. So if you use other choices for other attributes, it works the same. It works the same. Okay. And then if we count the fractions into the data size and also the P positive, P negative, it's fairly straightforward to apply the same formula to compute the entropy of each subset. And then one subtle hint here, when we compute the expected entropy, meaning we're gonna do the weighted average of these entropies across the subset, right? Remember, now it is weighted by a non-integer size, right? Why? Because data size is 5 plus 5, 14 for the sunny subset, 4 plus 4 over 14 for the overcast and 5 plus 5 or 14 over 14 for rain, right? So you need to divide this non-integer size over the total size, which is still 15, right? When you do the weighting, otherwise you might have some weird or unreasonable results when you do the homework one. Right? So just be careful. Right? So now I want to ask a question, right? So now if we switch to majority error, right? If you use majority error to majority error gain to select attribute and split the data set, and when we have some missing attribute, how can we compute majority error? Any thought? Yeah, the same one, right? So we just follow the definition and use the same one. Like if we take a look here, right? You have two positive examples, 3 plus 5 or 14 negative examples, right? What's the majority label? Negative, right? So if you use negative label to predict all these 5 plus 5 or 14 examples, what's the error? 2 over 5 plus 5, 14, right? That's it. Right? It's following exactly the same way. Okay? And similarly, you can, under this strategy, to compute Gini index. There's nothing different. Okay, this is for the training procedure. As we mentioned, right, when we can break one example into several fractional examples, and for each fractional example, we can complete the missing attribute with one particular value. So we kind of have like complete coverage of all possible choices and throw them into our training algorithm. But what about test? What about test case? Suppose in the test case, you have met a example like this, right? Your tree is there, right? But you have a test example, you don't know the attribute outlook. How can we make prediction? Yeah, exactly, right. So we actually follow the same way, right? We still break them into three fractional examples, where each example takes attribute to be a different value. Right now we have some we have the attribute complete. We can throw them into our classifier, right? Our decision tree. Then suppose we have from the three prediction, we have two are positive, one is negative. We just vote the final prediction based on their fractions and pick the one who got the largest vote. They'll got final prediction. No, it's based on training set. Yeah. But of course, if you usually we're based on training set because we assume, okay, we kind of you're coming one test data set, I'm gonna give you a prediction. You're not assuming, okay, I know all the other ones test cases. If you're knowing other ones test cases, of course you can do that. Okay? But for the most general case, let us use the training case, right? And then you just look at the weighted majority and who gives the larger vote of the prediction, you give that prediction. Right? Okay, yeah, let's stop here. So I think after today's lecture, you have full knowledge to finish every problem in homework 1. So if you haven't started, please start right now and don't wait until next few days. That will make you feel really painful and stressed. Okay, see you on next Tuesday. Yeah, that's good. You just look at you just do this one by one. Yeah. And And if one example happens to have two missing attributes, things will become more complicated. It's like you first break them into fractions, right? And one fraction example might have another missing attribute. You're going to break them into another fraction. So that will be much more complex. Right? But this is just one ideal option you can use. And the most common choice is just I just look at which one is the most common one and just use that. Yeah. Okay.